In this example, we're looking at a plate of thickness delta, and it's heated by both internal heat generation Q dot, which is a volumetric heat generation, which has units of watts per meters cubed, and irradiation G. It is cooled by convection to a fluid, by radiation to the surroundings, and conduction to a base containing a fixed temperature T0. We want to assume a uniform temperature in the plate of T sub plate, steady state conditions, in that the thickness delta is much smaller than its width L and its depth into the page W. So our goal is to find delta in the terms of the other parameters. So following our routine that we explored with the first example problem, we can state that we're given everything in this problem except for delta, since we're solving for delta in terms of the other parameters. So we can say we're given H, T infinity, G, alpha, epsilon, Q dot, T surroundings, L0, K, T0, L, and W, and T plate. And we're trying to find delta. So our schematic is already provided for us. Which means we can then jump to our assumptions. First, we know that this is under steady state conditions. So the first assumption is steady state. Second, we can assume a uniform temperature in the plate of T sub plate. This is important because it means that all the surfaces of the plate are at the same temperature, which is T sub plate. Third, since we know that delta is much smaller than the other dimensions of the plate, then we can assume then that there is negligible heat transfer out the sides of the plate. What this means is that all heat transfer is at the top and the bottom. So moving on to part 5, we first draw our CV. And our CV is going to be around the plate itself. And because there's a lot of activity within the diagram we have here, we're going to redraw the CV down here just for purposes of being able to show which way our heat is flowing. So for part 2, we're going to draw our heat vectors. And we know that we have irradiation coming in, we have generation inside, but then leaving we have conduction out of the bottom, and we have convection out the top, and radiation out of the top. Third, write out our first law, which is dECV dt, E dot in minus E dot out plus E dot gen. We know that it's steady state, so we can get rid of the dECV dt term. According to our diagram, what's coming in is going to be the irradiation. What's leaving is convection plus radiation plus Q conduction. We know that what's being generated is going to be Q dot times the volume. So what this means then is we can rewrite our equation as 0 is equal to Q irradiation minus Q convection minus Q radiation minus Q conduction plus Q dot times volume. Fourth, we can apply our heat transfer laws. What this means is that we can then replace these Q's with some functions of temperature. So first, let's look at Q irradiation. You can see the irradiation happens on the top of the plate, which means that we know that only some of that irradiation is going to be absorbed by the plate, and that's going to be alpha times G. The area that it's acting over is going to be the length of the plate times the depth into the page. Convection will be H times the area it's acting on, which is L times W, times the temperature difference, that of the plate minus the fluid, since we have the arrow being drawn from the CV out to the surrounding fluid. So it'll be T plate minus T infinity. Q rad will be the area at the top of the plate, which is L times W, times epsilon times sigma, times the temperature of the plate to the fourth minus the temperature of the surroundings to the fourth. And Q conduction will be K times the area that the conduction is acting through, which will be L times W, divided by the length it's traveling, which is L0, times the change in temperature, which is going to be T plate minus TO, based on the fact that conduction is leaving the control volume. So plugging these numbers in, we can then write out our equation in terms of temperature and other parameters. So 0 is equal to alpha times G times L times W minus H times L times W times T plate minus T infinity minus L times W times epsilon times sigma times T plate to the fourth minus T surroundings to the fourth minus K times L times W over L0 T plate minus T0. And finally we have Q dot times the volume of the plate, which is just the area at the top of the plate, which is L times W times the thickness delta. So what this allows us to do is to solve it in terms of delta. And we can recognize that each term in this equation has an L times W, which means that they can all cancel out. So if we do that, we get 0 is equal to alpha times G minus H times T plate minus T infinity minus epsilon times sigma times T plate to the fourth minus T surroundings to the fourth minus K over L0 times T plate minus TO plus Q dot times delta. And then further solving for delta, we get our result. Delta is equal to negative alpha times G plus H times T plate minus AT infinity plus epsilon times sigma times T plate to the fourth minus T surroundings to the fourth plus K over LO times T plate minus TO, all of this divided by Q dot. So finally, we want to evaluate our results. And essentially, we can see here that as you increase Q dot, then your plate is going to get thinner. And the reason why is because if you increase the Q dot, that means that there's more heat being generated in the plate, which means that you want a smaller volume of the plate to release the heat by convection, conduction, and radiation. You can also see then that as you increase the amount of cooling provided to the plate through the forms of conduction, convection, and radiation, then you can get a larger thickness of the plate, which should also make sense because that means a larger plate is going to have a larger energy generation, which means you can then release more heat out to the surrounding.